Hello and a warm welcome back to Mr. M for Chem IB Chemistry channel. Hope you're all doing well and in good spirits, ready to rock and roll with some acids and bases chemistry. So first of all, we've got a strong acid and a weak acid reacting both with equal amounts of magnesium. They're both the same concentration. One takes longer, one takes shorter. One goes a higher temperature, one goes a lower temperature. Clearly the higher temperature and the one that goes faster is the stronger, and the converse is true for the weaker. What the students tend to mess up, they tend to forget that the same concentration will react with equivalent amounts of magnesium, but it will take longer with the weaker acid. The weaker acid that we can continue to explore with conductivity, the extent of dissociation. If it's greater dissociation, it's a stronger conductivity. Let's rock and roll. Hydrochloric acid, bright light, beautiful bright light. Hydrochloric acid, complete dissociation, strong acid, beautiful. Are you going to rinse your electrodes? Honestly, scruffy chemist. Weak acid, ethanoic acid, incomplete dissociation, partial dissociation, a dim light because there are less ions in solution. The same is true for bases. Sodium hydroxide, nice strong base, complete dissociation, bright light, and he's not going to rinse the electrodes again, honestly. And ammonia, a weak base and a very dim light. You can just see that little faint orange up there. I can see it, you can see it, beautiful, move on. pH probe and universal indicator paper. Okay, if an acid gets less strong, it gets higher pH, and the converse is true. Students mess that up all the time in exams. So let's have a look. The colour of universal indicator for ethanoic is orange. And the pH, I put as 2.2. These take a little while to settle down. The probe is not the newest of probes, but I lost the will to live around about 2.2. Okay, you're going to rinse the probe this time? Yay, proud of you. So, rinse the probe. Now, into the strong acid, hydrochloric acid, it goes red. Universal indicator is red. And the pH, well, if pH is minus log to the base 10 of the hydrogen ion concentration, minus log to the base 10 of 1 is 0. So this should be 0. Is it going to get to 0? Go. Come on, you can do it. This assumes two things. The stock solution was fresh. The pH probe is calibrated. Neither of which are true because I got bored at 0.73. But pH 1, if you do the sum, is 1 mole per decimeter cubed is pH 0. Now we've got ammonium hydroxide, it goes blue. In fact, the ammonia is actually very good at dissolving the universal indicator blue coloration, which you can see seeping into the solution there. And when do I lose the will to live? 11.8, right? Take the probe out, give it a rinse in the distilled water. Good man. And finally, sodium hydroxide. It looks exactly the same blue as ammonia. It does, freely admit, but the sodium hydroxide should be a deeper blue. It is indeed stronger, and we can see that using the pH probe that it's going to rest, I think, if memory serves me correctly, at 13.80. Yay! Next. Come on, things to do, people to see, move on. What's next? pH scale. pH plus pOH is 14. As you can see there, pH 0 is a 1 mole per decimeter cubed solution of hydrochloric acid. So anything greater than 1 mole per decimeter cubed is less than 0, the end of the pH scale. Let's have a look at strong acid, strong base. First of all, is that meter going to behave? It's not behaving. I'm getting a nice pink coloration. The phenolphthalein goes into the solution at the bottom, an idealized graph, and then my graph looks, it looks identical to the one that's from the textbook. Let's try that with a weak acid, ethanoic acid, sodium hydroxide. Can it look like this one? This one? No, it doesn't. That's why I made my video small and the picture large. Notice the pH starts at a higher pH, it's about 3. We've got a long buffer region. The equivalence point is higher because of hydrolysis. That's a different video. Comment, like, subscribe at the bottom.